Okay, this video is about practical limitations on the discrete time Fourier transform. Okay, I remember when I first saw the idea of a discrete time Fourier transform, I thought, oh great, we can numerically approximate any Fourier transform we want, so we can analyze any signal that we want using a DTFT. Well, there's limitations about that, and we need to talk about those. So this again is in section 1.5.1. All right, so we're talking about, sorry for that jumping around. We're talking about 1.5.1 where we're looking at the discrete time Fourier transform. And we were going through these 6 items that show up in this section. So item number 5 is practical approximations. Okay, so if you think about it, if you want to compute a spectrum using a computer, you have a couple of things that have to happen. Number 1 is you can only use a finite number of time samples. Okay, so if you think about that, think about a cosine signal. If you wanted to analyze a cosine signal using the discrete time Fourier transform, you'd be hard pressed to do it because it starts at minus infinity, it goes out to infinity. So all you can do is take a finite number of samples of that and hope that that can be representative of the spectrum of x of t. Okay, well it turns out it can be representative of it, but the spectrum will be distorted because you're taking a finite number of samples. There'll be something that happens called smearing and leakage of the spectrum. All right, so I wanted to talk about that a little bit. Okay, so you think about that. If you had x of t and it had infinite support, okay, meaning it goes from minus infinity to infinity, is non-zero for that whole range. Okay, so think of something like a cosine. It goes on and on and on forever and ever and ever. Okay, but if you wanted to analyze this using a Fourier transform, you effectively have to multiply it by some finite window. Okay, so let's make this a 1. Let's make this some analysis duration TA. All right, this is the cosine function. What we'd really be analyzing is y of t. So y of t is going to be x of t multiplied by a unit step that turns on at t and it turns off at t minus ta. Okay, so if we wanted to find y of f, all right, we're talking completely in the continuous time here because this is relevant. If you wanted to analyze this and you can only look at a finite duration and sample it, and you can use a computer to compute the spectrum, you'd be effectively doing this kind of operation. You'd take x of t and you'd multiply it by this pulse. Okay, so what is multiplication in the time domain? Okay, multiplication in the time domain is convolution in the frequency domain. All right, so think about that for a second. We're used to going the other way around. We have convolution in the time domain, and it becomes multiplication in the frequency domain. So that's what we're used to looking at. X of t convolved with h of t. You take the spectrum, you get x of f multiplied by h of f. We're going the opposite way. We're multiplying in the time domain, which turns out to, by duality. Duality is something you should have talked about in signals and systems, but by duality, this is going to be x of f convolved with p of f, where p is this pulse shape. Okay, so it does distort the spectrum. All right, so I think in an ideal case, we're not even talking about replicating the spectrum yet from sampling, but think about that. If I had x of f convolved with p of f, well, I know what x of f looks like if I'm looking at a cosine. It's just frequencies f naught minus f naught on the f-axis with a weight of oh shoot, I can't remember the weight on that if it's in the F domain. So let's change this to capital omega. Alright, so here's the omega axis, omega naught minus omega naught. The weight on here is pi. Alright, so I'm going to take this signal and I'm going to convolve it with a pulse. Okay, so if I just drew the magnitude of it, you know, there's a shift on this that would generate a phase component. Let's not worry about that. If I did this, I would get a sinc function for the Fourier transform of the pulse. Okay, so you should have known that from Signals and System. You can go back and brush up on that. Alright, and another result that you had from Signals and Systems is that if you convolve anything with an impulse function, so here's a couple of impulse functions sitting out here. If I convolve this with the impulse function, it simply relocates the spectrum to be centered at the impulse. Okay, that's a time domain result. That's also a frequency domain result. Okay, so what I would do here is I expect a spectrum with very thin spikes representing a cosine, but what I get is something that looks like this. I'm kind of condensing the scale because that's what would really happen with a practical omega. Okay, so I'm expecting spikes. I'm expecting spikes right here and here, but what I get is something with a little smearing and what we call leakage. Okay, so it leaks out the sides here because of the finite window. Alright, so we're going to talk a lot more about this because if we're going to do analysis with FFTs and DFTs and discrete-time Fourier transforms, we need to understand what's happening here. So that's our first introduction. So let me summarize that. Okay, for practical sampling, you have to have a finite number of samples. Okay, so that means you have to truncate the signal. So if you have an infinite signal, you have to multiply that infinite signal by a pulse and only pick up a finite window. Then you can sample that and do the analysis, but that's equivalent to multiplying by a pulse. Okay, so we have x of t times a pulse, which means in the frequency domain it's a convolution of the original shape of the spectrum with the pulse shape. Okay, and then I would give an example of a cosine. Cosines have these spikes. Alright, if I convolve a spike with the pulse shape, I end up with this kind of picture. Does that tell me that there's energy at omega naught and minus omega naught? Yes, it does. I just have to know what to expect to see, because you would also think, oh, there's some energy at these side lobes. No, that's not really there. That's a consequence of taking a finite number of samples. Okay, so that's our first introduction to this. You'll have to think about that and hopefully understand this trade-off that we're going to be doing when we do DFT analysis.